Welcome back to my favorite people. In the last two lectures, I went through nucleophilic substitution reaction SN2, and I said that we have four factors that we need to include them in our calculation to figure whether the reaction is going to be fast or not. One was the steric effect. As it goes up, reaction will be slower. The nucleophilicity, the stronger the nucleophile is, the faster reaction will be. And the third one will be solvent. And fourth is temperature. And I'm going to try to go through the third and fourth one in this lecture, if it's possible. Okay, we're going to start with polar protic solvent. Polar protic solvent is the solvent that is polar. And as you see here, we have electronegative elements like oxygen or nitrogen attached to carbon. And because they are more electronegative, they will pull electrons to themselves. They will get a negative charge, partial negative charge, and partial positive charge. Those partial positive negative charges are permanent. So we have permanent charges, and that's the reason we call them polar. But there is no acidic H attached to, to attach to the electronegative element. So I'm going to call them a protic. So a protic solvent has no acidic hydrogen. Okay, has no acidic hydrogen attached to the electronegative element. Okay, well, the protic solvent, the protic solvent, if you look to electronegative element, it has hydrogen there. So they are not only polar, they do have acidic H. So X attached to H, and this is gonna be the acidic hydrogen. Okay, and this is the difference between protic versus a protic. Protic has acidic H, while the protic no acidic H. Okay, now let's see effect of that, acidic H, or in the absence of it, on SN2 reaction. So first one, I go with a protic solvent like methanol, and my nucleophile, I go methoxy. So this one, it will be methyl attached to oxygen. We call it methoxy. Okay, and if you want to say it has a negative charge, you will raise that one. And you say this is going to be methoxide. Okay. The methoxide, it has a negative charge. Okay, it's going to try to stabilize the negative charge somehow. And if you have a polar solvent, your polar solvent, if you have a protic solvent, the protic solvent is going to have acidic H. That acidic H, it will give some electron density to oxygen or nitrogen, and it will have positive charge. Now, oxygen on the methoxide or the nucleophile will go after this hydrogen, and it will establish interaction with it. So technically, we get hydrogen bonding. And now what will happen? I'm going to say that lone pair now is shared with hydrogen. Okay, so that lone pair got shared with hydrogen. Means the charge on the nucleophile got dropped. The nucleophile got more stable. So our nucleophile got more stable. Okay, so you think that's a good thing, okay? And so my nucleophile got stable, that should be fine, okay? Nothing wrong until now, okay? Nothing wrong until now. But if your nucleophile gets more stable, it will be less reactive. Okay, if it's less reactive, it will give you slower reaction. Okay, so the nucleophile gets stable, and because it's stable, it will be less reactive. If it's less reactive, the reaction will be slower. Okay, same nucleophile. Let's take it to a protic solvent. And our protic solvent, I go with DMSO. Dimethyl. We have sulfur, we call sulfoxide, and the name for it is DMSO. Okay, now I have the same nucleophile. This is exactly same nucleophile. There is a negative charge on oxygen and positive charge on carbon. Okay, so exactly same nucleophile. And again, we have -1 and oxygen. And you have to ask yourself, what is the negative charge on the solvent? The negative charge is located on sulfur, and sulfur is buried with two methyl groups and also oxygen. Remember that the structure is going to be like this. You have two carbon, and those two carbons, they have three hydrogens. And this one is, forgive me, that's sulfur, not carbon. So if you want to reach positive charge from this direction, it's going to be hard. Why? Because you will see two methyl groups. And if you, again, if you reach it from this side, you will see this group, or say that group. And that steric effect will make it harder for sulfur to technically pull some electrons from the nucleophile. And because the nucleophile, or oxygen on the methyl side, will have harder time to see sulfur, so it's not going to get stable. Okay, this is not going to get stable. So you can write this in protic solvent, nucleophile will not get stable. Okay, in a protic solvent, nucleophile will not get stable. It will not be stabilized. Okay, and because it doesn't get stable, it will be more reactive. More reactive. That means the reaction will be faster. So you get a faster reaction. Okay, now let's show all those, like highlighted points on this graph. I have methoxide reacting with alkyl halide. We are kicking the halide out of the system, and we get oxygen and getting a bridge between two carbons. So normal condition, if you have, let's say, the protic solvent, because this piece is going to get stabilized, it will be okay. Or you can say the hydrogen, the negative charge gets distributed. I'm gonna say this, if this is okay, if this is level of the reactant, okay, for a protic solvent, for a protic level is gonna be here, and this one for a protic. Okay, now let's connect it to the reactant and to the product. Forgive me. I'm going to try to go through the same transition state and say this one is the pathway. Okay, I got that. I'm trying to follow the same transition state. No, so I think I need to do it for myself. So let's say, okay, cool. My bad. Okay. And when you have a protic solvent, the activation energy is going to be this. This is the activation energy. Well, when you have a protic solvent, because the nucleophile get more stable, the activation energy, it will be bigger. So activation energy for protic in a protic solvent, activation energy in a protic solvent is higher than activation energy for a protic solvent. And because the activation energy is less when you have, for example, DMSO, the reaction will be faster in DMSO than methanol. Okay, that's about the reactant. Nucleophile gets more stable and then more stable inside the protic solvent. That means that the gap between reactant and the transition state gets bigger. Okay, you might ask this: how about the transition state? And why don't you talk about the transition state? And what's the effect of the solvent on the transition state? Let's review the transition state. Okay. So this is going to be our transition state. We have carbon attached to, let's say, hydrogen. Okay, another hydrogen here. Okay, I go, that's, for example, hydrogen. And let's put hydrogen down there. Okay, next. We have a methoxide is coming to the system. So I go CH3, oxygen, and oxygen is trying to share lone pair with carbon. At the same time, I have the chloride is taking lone pair. Okay, so it's taking those two electrons technically and trying to leave the system. And just to be more accurate, is taking both electrons. Okay, now chlorine has a negative charge, oxygen has a negative charge. Where is the positive charge? On carbon. The positive charge is buried exactly there. Okay, right in the right on carbon. Okay, now where is our solvent? Our solvent can be anywhere. Okay, let's say we have a polar. Okay, we have a like say we have a polar solvent. Okay, the polar solvent, okay, it's not gonna technically, polar solvent is not gonna be able to reach carbon and stabilize the transition state. Why? Because it's buried. Okay, polar solvent, listen carefully. Polar solvent, it cannot reach carbon because carbon is buried. It cannot stabilize it, but it can stabilize the nucleophile and drop the active reactivity for it. Okay, how about the DMSO? Okay, DMSO, non-polar, like in a protic solvent. This is DMSO. Okay, DMSO, it has negative charge here, positive charge there. Okay, and so can we use the negative charge on oxygen to stabilize the transition state? Again, it's the same issue. The positive charge on carbon is hidden at the center. We cannot really reach it. So I can easily say this: effect of solvent on stabilizing the transition state is not much. Okay, is not much. Why is not much? Because the positive charge is buried by the substituent, like 2 or 3 hydrogens, and also leaving group and the nucleophile. And because it's hard to reach carbon, transition state is not, the energy of the transition state is not going to change dramatically in a protic versus a protic solvent. And this is the reason I kept the transition state almost the same level. Okay. Now, the fourth factor, it will be the temperature. And what's going to be effect of temperature on SN2 reaction? So we are studying SN2 reaction. Remember, in order to have SN2 reaction, we need to have two components. One, the substrate, and this is going to be the substrate. And the second one will be the nucleophile. Okay, so I need to have 2 of them. Okay. And in order to have SN2 reaction, I need to have collision between them. Okay, so I need to have a collision. And now, if I increase the temperature, rate of collision will go up. That's completely reasonable. As we increase the temperature, velocity will go up. So I expect to see higher rate of collision. And so I'm going to say, and if you run the reaction in 2 different temperatures, the one with higher temperature should be faster. And this one, it will be faster. That's completely fair. And your product will be this. You get alcohol plus chloride. Again, here you get alcohol plus chloride. Okay, but there is a hidden point in these two examples, and the hidden point is this. Okay, carbon, the alpha carbon, this is the alpha carbon. Carbon in this case it doesn't have a beta, it's not connected to another carbon. That means we don't have beta hydrogen. There is no beta hydrogen. Okay, so be careful. We have only alpha carbon, and there is no beta carbon there. Okay, what will happen if we get a beta carbon? If there is a beta carbon, so this is alpha, and that one is gonna be the beta. Okay, so like low temperature, I'm gonna assume this is gonna happen. SN2 reaction, the nucleophile will go after the alpha carbon. It will kick the chloride out of the system, and this is gonna be my product. Temperature is really low, so I'm going to say this is going to be SN2, simply nucleophilic substitution, and nothing surprising. Now, what will happen if I increase the temperature? Let's say we increase it to 50 or 100 degrees Celsius. In that case, you will be dealing with, okay, you will be dealing with maybe elimination reaction. Why? Because you have a beta carbon that does have hydrogen attached to it. Okay, so if you increase the temperature, you might get same product like first reaction that you got. This is going to be your first product maybe. So you get alcohol plus the chloride. Also, you might get this. So this one it will be SN2 reaction. You might get E2, elimination reaction. And the elimination reaction, in this case, nucleophile will go after hydrogen. While we are breaking this bond, these two electrons, they will be given to carbon, and then carbon, it will give them to chloride, and we get this. We get the alkene plus H2O plus Cl minus. So we got alkene or elimination of product. As you increase the temperature, the SN2 reaction might start shifting to elimination, okay? And you need to be careful about it. If there is a beta hydrogen there, okay, nucleophile on high temperature might go after the easy target. And the easy target, it will be hydrogen. Take hydrogen and leave the system and get and turn to a neutral compound like water. So I will have two reactions running at the same time when I increase the temperature. One, it will be SN2 reaction, and the second one, it will be elimination. And the elimination will not happen unless you are dealing with high temperature. Usually high temperature is going to favor elimination, okay, usually. And again, nature of the nucleophile also will affect ratio of these two products. And at the end of this chapter, we're going to practice more example about how to differentiate, reaction like SN1, SN2, E1, or E2. But for now, I'm going to stop the lecture here, and thank you very much.